Welcome, everyone. Pongwei Ko is joining us from Stanford today. He's advised by Percy Lang. He studies the theory and practice of building reliable machine learning systems. His work has been recognized by a number of awards, including Best Paper Awards, ICML, and KDD. And prior to his PhD, he was the third employee and director of partnerships at Coursera. So an interesting background. Before he gets started, I just want to mention, please feel free to ask clarifying questions during the talk. You can put them in the chat or interrupt, but please hold all other questions to the end. Thanks. So Pongwei, why don't you take it away?
Thanks, Kevin, for the kind introduction, and it's a privilege to be here at UW. All right, I'm excited to tell you about my work on making machine learning more reliable. So today, machine learning systems are widely deployed and deeply embedded into our daily lives. So they're used in our phones, like for face recognition. They're on our roads in autonomous vehicles. And they're even in our hospitals, used for diagnosis, early warnings, and treatment recommendations. These machine learning systems are out there and touching millions and millions of lives every day. And on one hand, this is really exciting. There's so much potential across these applications. But on the other, it is also extremely risky because these systems have failed, and the consequences of their failures are magnified by their reach. So let me give you some examples. Models can fail when they're deployed in different environments from what they were trained on. So the healthcare company Epic, it uses machine learning to generate early warnings for patients at risk of sepsis, which causes 1/3 of all deaths in US hospitals. Epic trained its model on patients from 3 hospitals and showed that it worked, and then deployed it to hundreds of other hospitals. But these environments are different. Different hospitals have different equipment, different protocols, and so there's a shift in the data distribution. And in these new environments, the model missed sepsis most of the time, and instead caused a lot of alert fatigue from false positives. And this was pretty shocking, right? By the time the study was published last June, the model had already been deployed in hundreds of hospitals. And so what other failures might we be missing? Models can also fail on different subpopulations of the data. So for example, prior work has shown that face recognition models can do substantially worse when we shift from lighter skin to darker skin people. And such failures can have serious consequences. And so these systems, whether we like it or not, are already being deployed in applications like policing. And these systematic failures on particular subpopulations can exacerbate existing problems and inequalities. These subpopulation failures are not limited to demographics. So for example, satellite images are commonly used for mapping and disaster response. But some subpopulations, in this case regions, might have much more training data available than others. And so in the Americas, for example, a model might do well. But when we shift to looking at Africa, we show that it could do much worse. Compounding these failures is the fact that our models are often complex and opaque and trained on millions or billions of data points. And so even if we know they fail, we might not understand why or how to fix them. These are urgent problems, and because machine learning systems are already out there in the wild. The horse has left the barn, but our research is only just starting to catch up. And so I want to tell you today about my work on tackling these problems, on methods for understanding model predictions and for building models that are more robust to shifts across different subpopulations and different environments. Okay, so here's the outline. We'll start with methods to better understand model predictions. Okay? For example, if we realize that our model has made an error, can we diagnose why? Fundamentally, machine learning models come from their training data. So I'll talk about how to trace a prediction back to its most influential training points using classical tools called inference functions. Okay? And this idea of finding influential training points is a core primitive, and I'll show how our work on this has enabled many downstream applications. Then we'll move from understanding the training models that are more robust to shifts across different subpopulations. This is an important problem, as we saw, and models can fail on important subpopulations like particular demographics or regions. And so to tackle this, we'll use techniques from distributionally robust optimization to directly optimize models to do well on each subpopulation. And we'll show that this can substantially reduce disparities. In the third part, we'll zoom out to consider distribution shifts more broadly. These shifts are when a model's training data distribution, it doesn't match the test distribution that we want to evaluate it on. And it includes the subpopulation shifts that we just talked about, as well as shifts in environments, like between different hospitals in the sepsis example. These types of real-world shifts are unavoidable in the wild. And we'll see many examples throughout this talk. The problem is that despite their ubiquity, they are understudied in machine learning research. And this is because the notion of a distribution shift is very broad. It's just anything where the train is not test. And so prior work on distribution shifts has focused on shifts that are quite different from the examples we've seen. For example, it's common to study style shifts, right? Like going from photos to sketches in the DomainNet dataset and other similar datasets. And these are interesting shifts. So a lot of work has gone into developing methods to handle them, like the fixed match training algorithm from Google, which uses unlabeled data to adapt to the test distribution. And it does really well on DomainNet. The question that we were interested in, however, was how well the success on these existing benchmarks transfer to shifts in real applications, like shifts across hospitals or farms or wildlife cameras. Right? These shifts are very different. And so how well do algorithms like fixed match actually do on these other shifts that we care about? So to answer this question, we constructed the WELS benchmark, which captures a variety of shifts that arise in real applications. And this benchmark has now been widely adopted, and I'll tell you more about it and answer to a question in the third section. Okay. And then talking about applications, I'll wrap up with a deeper dive into COVID-19 modeling, right, which is challenging because the environment keeps changing. Right? For example, there might be new policies that affect transmission, and because different subpopulations have been affected very differently. And so I'll talk about how we tackle this end-to-end, from acquiring better data all the way to building more reliable decision support tools that help to inform policymakers nationally and internationally. All right, so that's the overview. And each project focuses on making a different facet of the machine learning pipeline more reliable, from understanding existing models to training models that are more robust across subpopulations, evaluating them on realistic distribution shifts, and finally translating them into actionable insights. Underlying this work is my goal of making machine learning more reliable by anchoring to real-world applications, extracting the core problems, and then formulating them in a way that lets us develop more general methods and tools. And we'll see this theme throughout the talk. Okay, so let's dive in. We'll start with how we can understand models through their training data. The motivation for this project came from back when I was an undergrad. I wanted to learn more about machine learning in medicine, and so I signed up to shadow an oncologist, Dr. Lei, shown here, at the Stanford Cancer Center. As part of that, I got to attend a few tumor boards, which are meetings where specialists discuss difficult cases. And I was struck by how often the doctors were using prior cases to explain their reasoning. This experience stuck with me, and it became the first project of my PhD. I was reading about existing techniques for explaining models. And unlike the doctors' focus on prior cases, which is essentially the training data, most techniques just ignore the training data. And so they treat the model as fixed, and they focus instead on the test data. For example, they may ask, which parts of the test input most affect the prediction, leading to heat maps like this. Many such methods have been developed and have proven very useful, like Lime and Shep from UW. right? But they ask a different question, and they don't study how the model and its predictions derive from the training data, which is fundamentally where it comes from. And so that's where our work comes in. Inspired by the clinicians, we studied how to inspect the model in terms of its training data. Compared to looking at the test data, this is difficult because training is more complex than inference or evaluation. And here we want to invert the training process. But it enables many other applications, such as debugging our training data, which might be corrupted or mislabeled or biased in some way. So how might this work? To continue the cancer setting, say we have a model that takes in a tissue patch, and in this case, it predicts that it's normal. So only a 35% confidence that it contains some tumor cells. And however, say we discover that this is wrong, right? These are actually tumor cells. And now we want to investigate why the model made this error. In this example, it's actually because one of these training images was mislabeled. Okay, so you can take some time to guess which one. But even with just the 4 images here, it takes a while. And it's hard to manually inspect all of the training points. But if we can find the ones that were influential on the prediction, right, then we can focus on them and find our culprit more easily. Okay. So how can we formalize this idea of finding influential training points? A natural thing to do is to take a leave one out approach, which has been around in statistics since the 50s. This means that we'll leave the first training point out and then retrain the model and then quantify the influence of this first training point on the test point by the degree to which the prediction changes. Okay, so in this case, it's -4%. And then we can repeat this process for the second training point, -2% this time, and the third, and so on. And so in this example, removing the third point, which was mislabeled, would flip the model's prediction. And in this way, we can quantify the influence of each training point. The problem is that it is too slow to repeatedly retrain the model for every training point. And so to tackle this, we are going to approximate the effect of retraining with what's known as influence functions. All right. So to see how this works, we'll introduce weights on the training data. Originally, each training point has an equal weight of 1. And when we leave a training point out, that's equivalent to setting its weight to 0. So visually, this purple dot on the x-axis is the original model where we don't change the weight. And so the change in the prediction on the y-axis is 0. Right? And on the left, this is what we want to estimate, the actual change in the prediction as we take the weight on the training point from 1 to 0. And the problem is that computing this by retraining the model is slow. Instead, we can view the weight as continuous and then compute the gradient of this curve and extrapolate it out. Okay. So this is the first order Taylor approximation. And surprisingly, even though it needs to account for the whole training process, we can compute it in closed form using influence functions. Okay, so what does this approximation look like? We'll start with this quantity, which is the loss of the original model, theta hat, on some test point z-test. So you can think of the loss as a measure of how accurate the model is on some point. And then this quantity on the left is the loss of the new model that we get after we remove a training point z-train and retrain the model. All right. So overall, this is the change in the loss on the z-test after removing z-train. So that's the left-hand side is what we want to calculate. And on the right-hand side, we have the influence function approximation, which is an inner product between the gradients of the model's loss on the test and training points with this inverse Hessian in the middle. And the specifics of this are not that important for this talk, but I want to highlight 2 things. So first, this is a closed form approximation that doesn't involve retraining, which is pretty cool. And second, this inner product defines a model-based similarity metric between data points. So we can view the orange term as the model's representation of the test point. And likewise for this green term, And then this metric in the middle captures the effect of all of the other training points. So this gives us a similarity metric that's tailored for the model and that we can use in downstream applications. These influence functions were developed in the field of robust statistics in the 70s and were originally used for measuring the variance of estimators and robustness to outliers. So there are some challenges in adapting them from this classic setting to the modern machine learning setting. So for one, the data sets today are much larger and higher dimensional. And so there's still computation challenges, especially with the inverse of the Hessian matrix. So in our work, we build on classic tools from optimization, like conjugate gradients, as well as more modern stochastic estimation methods to try to compute this efficiently. And it works quite well. Okay, so the estimated change using influence functions lines up with the actual change in many settings. It's a bit messier for more complicated models, but the overall correlation still holds. Okay, this figure represents removing single training examples, which is what classical work almost exclusively studies. However, in practice, we often want to remove a large group of points. Okay, so for example, to check if a particular environment, like a hospital, is skewing our predictions, we might want to remove all of its training data. And such large perturbations to the training set are a challenge for first order approximations. Classical theory would expect it to break. And so in follow-up work, we tried removing large coherent groups of training points up to 25% of the data set. And we found that there was still a surprising amount of correlation between the estimated and actual effects of removing groups. So this means that influence functions can still accurately rank influential groups of points. And also, this setting is quite far beyond the limits of classic asymptotic theory, which studies when the estimator is accurate. Right? That is when these dots on the scatter plot are very close to the y equals x line, right? Which is not what is happening here. And so we developed some new non-asymptotic results, right, to explain this phenomenon by focusing not on the accuracy, but on the correlation. Okay, let me wrap up this section by briefly mentioning the implications of our work. Okay, so understanding predictions by tracing them back to the training data is a core primitive that enables many other applications. And we talked about debugging data sets, and in follow-up work, we also showed that influence functions can be used to expose data poisoning vulnerabilities. More broadly, there's been a ton of other work from the community extending or taking this idea in different directions and applying it to different problems. So we don't have the time to do this justice, but here I've listed some representative papers on how others have used this approach to build more robust models and to make them more fair and secure, including work from just last year from UDEP, from Sahil, Mike, and Renee on debiasing data to improve fairness. So that's the first part on studying the effects of the training data. One common issue with the training data is that it is skewed in some way. So for example, there might be some subpopulation that's a minority of the training data, and models might perform poorly on that subpopulation as a result. So now we'll turn to the subpopulation problem. And this is joint work with Sherry, Tatsu, and Percy from Stanford. So as we said, the problem is that models can work well on average, but poorly on some subpopulations that we care about. Okay? And in the intro, we talked about demographic subpopulations, like in face or speech recognition, and geographic subpopulations, like in satellite images. More broadly, we can also formulate many spurious correlation problems, like models getting tricked by image backgrounds as subpopulation problems. So to explain this, let me backtrack a bit. One reason why models are unreliable is that they can latch onto spurious correlations, which are these shortcuts or heuristics that work most, but not all of the time. So as an illustration, we say we are classifying whether a bird is a water bird or a land bird. We and others have shown that instead of learning to classify the bird, models can instead spuriously learn to classify the background. And this might work well on average because in the training data, we might expect most water birds to be against water backgrounds. But the model is not learning the right thing, and it would fail when the correlation doesn't hold up. Okay? So for example, if there's a water bird against a land background. So we can formulate this as a subpopulation problem by partitioning the data into these 4 groups. And indeed, on this data set, and we found that a standard neural net gets very high accuracy on the majority of the data, which is birds and matching backgrounds. But it does very poorly on the subpopulations where the backgrounds don't match. So in other words, if we consider these subpopulations, then models that latch onto the spurious correlation will suffer from high subpopulation error. So we can formulate the goal of not using the spurious correlation as one of achieving low subpopulation error. So how can we formalize these subpopulation problems? What we'll do is assume that each data point comes from a set of predefined subpopulations or groups that we care about, right? And our goal will be to obtain high performance over each of these groups, different demographics or backgrounds and so on. The standard machine learning approach, which is called ERM or empirical risk minimization, is to just minimize the average training loss. And this can lead to high performance on the majority groups, but poor performance on other groups that we care about. So instead, we're going to use additional structure in the form of annotations of these groups, G, on the training data. Okay, and test time is still the same. The model will just get to see the input X. These annotations let us directly optimize for the worst group loss, and that is the maximum loss over each of the groups. And so concretely, instead of minimizing the average training loss, which we saw earlier, we'll compute the average loss for each group in purple. And then we'll minimize the maximum across these group losses. So this is an instance of a distributionally robust optimization problem, or DRO. And so we call this the group DRO method. Unlike influence functions, DRO is a classical idea, right? This time from optimization and operations research, and it's been developed primarily for convex models on smaller data sets. So there are several technical challenges in bringing this idea to more modern machine learning settings. And so for one, there's some complexity around regularization, which I'm happy to talk about offline. Another problem is this max operation in blue. And so I'll describe some technical details just for this slide. So without this max, we would typically do mini-batch stochastic gradient descent, which is fast and scalable. But this max is over the entire data set. And so it makes it difficult to get unbiased gradients just from a mini-batch. And so in our work, we developed the stochastic optimizer based on classic techniques in optimization, in particular online mirror descent. And this optimizer is actually very similar to the standard SGD. The main difference is that it maintains weights on each group. And at each iteration, it updates these weights, and with worse performing groups having larger weights. Okay, and then it simply updates the model parameters using the gradient of this weighted loss. Okay, so this uses similar ideas to Claire and Jamie's active sampling work. And in our paper, we show that it is scalable, it converges as quickly as standard training with empirical risk minimization, and is guaranteed to converge in a convex setting. Okay, so this let us scale DRO to neural nets, and using it, we applied group DRO to several data sets. And so the waterbirds data set, a face data set with different demographics, and a text data set, multi-NLI, that with groups that's based on Sachin and Noah's work on annotation artifacts. And compared to standard training, group DRO significantly improves accuracy on the worst group, with only a small cost to average accuracy. And so by explicitly accounting for these groups, we can almost completely eliminate the disparities between groups, right, at least on these data sets. Okay, we've worked on some follow-ups as well. So we've tried to understand theoretically why performance might be worse on some groups than others, and why selective classifiers can do exceptionally poorly on minority groups. And we've also developed a more efficient algorithms for optimizing for the worst group. So overall, this line of work, I was one of the first to demonstrate these types of robustness gains using DRO, which has now become quite a common paradigm in machine learning. Okay. So as we were working on these subpopulation shifts, right, we realized that the challenge wasn't just to develop methods. It was quite a struggle to find good real-world benchmarks as well. And so I want to tell you now about this broader question of evaluations for subpopulation shifts and distribution shifts more generally. Okay. In particular, I'll talk about our work on wilds, a project that I've been leading together with my lab mate, Shiru. So as we saw in the intro, distribution shifts are when the training and test distributions don't match. And this includes subpopulation shifts, as well as domain shifts, or shifts in environments, like between different hospitals in the sepsis example in the intro. These shifts are everywhere in deployment. And so we saw some examples of subpopulation shifts earlier, like the satellite image data set. And now I'll give you some examples of domain shifts from our own work. So in wildlife monitoring, where we often want to deploy cameras in new locations. So we took a camera trap data set and we split it into an in-distribution training and test set on the left, and then an out-of-distribution test set on the right that uses different cameras. And we found that even state-of-the-art models suffered a large drop in performance going out of distribution. We saw a similar drop in an agriculture application of detecting crops in different farms, and even in classifying tumors in different hospitals. And so these distribution shifts are a serious problem in many applications. And one big obstacle to our progress on these shifts is that they are understudied in machine learning research. And so as we saw, prior work on distribution shifts has focused on very different kinds of shifts. For example, it's common to look at shifts from synthetic perturbations, like changing the colors of handwritten digits or adding noise to images. It's also common, as we saw in the intro, to study style shifts, like going from photos to sketches in DomainNet and other similar data sets. And a lot of research has gone into how to deal with these types of shifts, like with the fixed match algorithm that we mentioned earlier. But what we were worried about was whether success on these benchmarks would transfer to other real-world applications. And this is a really hard question to answer, and because there's so many different types of real world, right? Photos are real, sketches are real, but it'll be dangerous to assume without checking that progress on things like DomainNet would carry over to all these other kinds of shifts that we care about. So we set out to answer this question by constructing the wilds benchmark. Okay? To capture shifts across real-world applications, we talked to a broad set of domain experts about the shifts that they were grappling with in their applications. And then Shiru and I assembled an interdisciplinary team to find data sets and then curate, adapt, and standardize them in a way that reflected the real-world challenges. Okay. I wanted to give a shout out to Sarah since she's interviewing later at UW as well. We worked together on the wildlife conservation data set I showed earlier, and she's really great to work with. Okay, so this took us the better part of 2 years to build, right? But in the end, we put together a benchmark of 10 data sets, right, across diverse applications, and they each capture a shift that arises in the wild. Right? And these come with structure in the form of multiple training domains, rich metadata, and also a lot of unlabeled data to try to make this problem tractable. So the examples I've shown so far are all from here. And across these data sets, going out of distribution causes a large performance drop in standard models. And so these distribution shifts are a problem across these data sets. Okay, so now we are equipped to answer our original question, right? Does success transfer across these shifts? We benchmarked 10 state-of-the-art domain generalization and adaptation algorithms on wilds. And this includes fixed match, which as we saw earlier, does really well on DomainNet. But on these shifts in wilds, we found that fixed match could be even worse than standard training with ERM. Right? And that doesn't even use any unlabeled data. And the same was true for the other methods we tried: invariant risk minimization, domain adversarial neural nets, contrastive learning, and so on. All of them improved performance on DomainNet, but none of them consistently beat standard training on wilds. And so these results were a wake-up call for us. And methods that work well on other shifts actually do not work as well as we thought they would on these shifts in the wild. And I want to dwell on this point a bit. Okay, so benchmarks like DomainNet and ImageNet, they drive a lot of progress in machine learning. But we have to make sure that they capture the essence of the task we want to solve. And solving style shifts is great, but it's a different problem from the shifts in wilds. And so with wilds, we're taking this broad variety of shifts that arise in applications and bringing them to the machine learning community so that we can make more directed progress on these problems. If we try to put it all in one package that's accessible, right, to help machine learning researchers dive into these applications that they might not be familiar with. So, and what wilds was published recently at ICML last June, but we've seen encouraging signs of early adoption, including some of you that work on this list. And there's also been a growing community around these problems. So for example, we started a NeurIPS workshop on distribution shifts last year. It was well attended both by domain experts as well as methods developers. And so I'm optimistic about future progress here. Okay, the last project I'd like to talk about is on COVID modeling. Okay, this is based on a paper in Nature, and it's joint work with Serena, Emma, and Yuri from Stanford, Jaylene, who's an epidemiologist at Northwestern, and Beth and David, who are sociologists. Right. So the COVID pandemic has had an extraordinarily heavy toll on our societies, families, and individuals. And making things worse is that these impacts have not been distributed equally. And so some demographic groups, like particular racial groups or people who are less affluent, have suffered even more. Amidst all of this is a lot of uncertainty about how we should respond, what policies we should enact, because these policies, like closing businesses or schools, also have their own costs. And this is where COVID models can play a role. If we can estimate the impacts of different policies on the trajectory of the pandemic, then we can make more informed decisions. And this means that our models must make reliable predictions under changing environments, like if there's a sudden lockdown, how does that affect transmission? And it also means that our models should be reliable on different subpopulations so that they can accurately reflect the disparate impact of COVID. Unfortunately, classical epidemiological models cannot do this. Right? So they are typically only fit to coarse-grained inputs, like the total number of cases and deaths over time. And so they can't account for policy changes because they assume the past is like the future, or for different subpopulations because they just look at the total. Okay, so what can we do? We know that COVID spreads through contacts. If someone gets infected, and then they pass it on to the people they meet, and so on. And so the spread of the virus is modulated by this underlying mobility network of how many people are going to what places at what times. So what we'll do is augment our input by estimating this mobility network using anonymized cell phone data, and then using it to model the disease at a much more granular level. Specifically, we want to capture the movement between people staying in different neighborhoods to different places of interest, like restaurants or grocery stores. And so we want to estimate this network, which we can encode as a matrix, where each entry represents the number of visits from one neighborhood to one place. And we have one such matrix for each hour. All right. We estimated these using anonymized and aggregated cell phone location data from the company SafeGraph. And for the sake of time, I won't get into the details, but I'll mention one technical challenge, which is that this matrix that we want to estimate is very noisy in the raw data. And this is a general challenge with fine-grained data, which tends to be more unreliable. So our approach was to fuse other data sources to obtain accurate row sums and column sums of the true matrix. And then we would project the noisy matrix onto these marginals to denoise it. And so we use a technique called iterative proportional fitting, which is a classic method developed for census data in 1940. And I'll be happy to talk more about it offline. Okay. The end result is a set of networks like this, right, where the gray edges represent movements between neighborhoods and places of interest. Okay, and then we took these networks and extended classic epidemiological models to work on top of them. Okay, so essentially, we assume that transmission is a function of how many people are in each place at any time, and which we obtain from the mobility networks. And this leaves us only 3 free parameters for the model, which we fit with approximate Bayesian computation, basically a grid search. Okay, so to make projections, and this is Chicago, we fit the model to case counts in some training period. And then we evaluate it on a held out test set where the model still gets to use the mobility data. And so you can think of this as adapting to unlabeled test data in some sense, which allows the model to maintain a reasonable fit over time, even when the environment is changing because a lot of lockdowns are happening. Now, in comparison, a model that only uses aggregate mobility data without the fine-grained network does worse. And a standard model that doesn't use mobility data just overshoots completely because it cannot adjust for the changing environment. Okay. So a model definitely still has limitations, but it does let us estimate now what would happen if we introduce policies that would affect mobility. And we can estimate the impact of closing places or looking at neighborhoods that are higher risk. And so I'll show you 2 vignettes from our analysis. So first, we looked at changing policies, and we found that instead of complete lockdowns, if we kept places open but limited the maximum capacity, then we could prevent a majority of predicted infections while maintaining the majority of visits and therefore economic activity. And so this kind of analysis provides policymakers with more targeted tools to control infections without having to shut down everything. Here I'm using figures from the New York Times article on our work because their figures are much nicer than ours, but it's based on our model. And so going back to the question of disparities between subpopulations, our model also correctly predicted that neighborhoods with lower incomes would have a higher rate of infections. And this is purely from the mobility data. These disparities are reflected in the mobility data. So people in neighborhoods with higher socioeconomic status, or SES, we found that they were able to stay at home, whereas people living in poorer neighborhoods could not reduce their movements by as much. And for example, because they had to work in essential jobs. And so they're exposed to more risk. And furthermore, they also tend to visit smaller and more crowded places. And so as an illustration, here's a scatter plot of how crowded typical grocery store visits are as a function of household income. And we predicted that on average, a visit to the grocery store was twice as dangerous in a lower income neighborhood. So these findings help us understand the mechanisms behind these observed disparities and inform our efforts to mitigate them. We were fortunate in that our work got a lot of visibility. It was on the front page of the New York Times and Washington Post, and it helped to inform policymakers at the federal and state levels here in the US, as well as internationally. In a follow-up project, we worked with the Virginia Department of Health to design a dashboard based on our model, and that could interactively support their needs. And so overall, by expanding our input features, we can build models that can adapt to changing environments, that can account for different subpopulations and help to provide more actionable insights. Okay. All right, so let me sum up. Okay. We started by developing some general methods, influence functions for understanding predictions, and distributionally robust optimization to train models that do better on different subpopulations. And these involve taking sort of rigorous and classical statistical tools and bringing them into our modern machine learning settings. In the other half of the talk, we dove into the challenges of distribution shifts across a wide variety of applications in wilds, and then a more in-depth study of COVID-19. And here we're kind of going the other way, bringing the problems and challenges of real-world deployments into the machine learning setting. So these projects reflect my approach to building more reliable machine learning systems, to develop general methods that are still anchored to real-world applications. And beyond what I've discussed in this talk, I've also worked on training models that are certified to be reliable even when the data is poisoned, and for learning from explanations so as to avoid latching onto spurious correlations. And on the application side, I worked in a genetics lab on methods for denoising epigenomic data, and I've studied how to identifiably reconstruct time series data in the UK Biobank. This work is, by necessity, interdisciplinary. Right? It requires collaborating with domain experts to develop a deeper understanding of the applications and settings in which machine learning is deployed. But by doing so, we can uncover what problems we need to solve to make these systems reliable. And then we can take these back and formulate them in a way that lets us develop more general methods. Okay, so where do we go from here? I'm excited about two future directions. One is how to train models that are more reliable under distribution shifts. So as we saw, this is a hard problem. Right? And if we don't know anything about the structure of the shift, then we can't guard against it. So to make this tractable, I want to develop methods to collect and exploit information on the structure of these shifts. So this information could come from metadata, right, like what's shown here, which allows us to inject some domain knowledge about the shift into the problem. So for example, perhaps we could use it to learn models that are invariant along these dimensions. Right? And often even unlabeled data has some metadata, so they can be used together. Most previous benchmarks don't provide this kind of metadata, and so methods to use it aren't very well developed. And whilst we have this kind of metadata for many data sets, and I think we can do a lot here. And so as one example, our work on group DRO that I covered earlier uses metadata in the form of annotations of image backgrounds and demographics to learn more robust models. A different source of structure can come from natural language explanations, which I think is exciting just because of how rich language is. It's a building on some of my previous work. I want to use this language model or this language to steer the representations we learn and make them more robust to specific shifts. Right? So for example, by focusing only on the salient features that are captured in the explanation. And both metadata and explanations are widely available across many applications, like from the wildlife example here to even pathology or other medical settings and other modalities even. And so I want to develop techniques that can make use of this kind of auxiliary data to be more robust. And the current state of the art just throws away most of this data, and then there must be more that we can do here. The second direction I'm excited about is building more interactive systems. And because in many applications, models will not replace humans, but complement them. And so I want to build models that can achieve high joint performance together with their end users. And this can be quite different, right, from the standard paradigm of just optimizing for the model alone. It requires some shared understanding of the way that each side thinks. And Gagan and Sherry had a really nice Kai paper last year on the complexities of getting humans and models to work well together. So I want to build on my work on model understanding to provide hooks for effective interaction. Okay, so for example, we can think of the doctors at the tumor board like making a joint decision by grounding their discussion in particular prior cases. So beyond my work on inference functions, I've developed models that try to understand intermediate concepts to better interact with users. So as an illustration, we train an X-ray model that could make predictions like this with an accompanying reason based on the concept, and then take feedback from a human expert on that reason, and then update their prediction accordingly. And we show that this can achieve high joint performance. This is joint work with Tao and Steve, who are both at UW now. And I think if we can provide end users with such tools, right, to understand, debug, edit, and interact with our models, then I think we can make them much more reliable, especially if the environment is changing, because we can combine the adaptability of human users with the statistical capabilities of machine learning models. All right, so we started the talk, right, with how our models can be unreliable in different environments and different subpopulations. And we've seen many examples of these failures across different applications. And on one hand, this is an urgent and serious problem because these models are already out there and we need to fix them. But on a more optimistic note, it's also very exciting that machine learning has the potential to help in so many important applications, right? Diagnosis and treatment in medicine, modeling in public health, conservation, agriculture, disaster response. These are just examples from my talk, and there are many, many more. And so that's what I hope to enable through my research on building models that can extrapolate robustly to different environments. They can work well on all subpopulations and interact effectively with their end users so that they remain reliable across these applications, even when deployed in the wild. This talk is based on work with many amazing collaborators. Thanks for having me here and happy to take questions.
Thank you very much, Peng. We have some time for questions. Why don't we start off with Paul from the chat?
Really interesting talk. I had a question sort of on the early part of your talk. I was wondering how the techniques that you have relate to methods for differentially private machine learning, and if somebody's applied that, how would that impact what you're doing, and just the general sort of sense of the connections there. Thanks.
Yeah, that's a really good question. So they are related, and there has been some follow-up work on using these notions of influence as a measure of like local privacy. And the relation, I guess, is an intuitive one. So if we find that a training point is very influential on the prediction, then if we know the prediction, we might be able to back out whether or not that point existed, right? It's not always necessarily the case, right? So maybe there are 10 other points that could have been influential in the same way, right? So it might not always be the case, but it is very related, and there has been some work on this. This notion of differential privacy is also very related to robustness in the robust statistics sense. So influence functions were originally developed in robust statistics and used to measure like the effect of a particular outliers, right, on the model. And so a model is not robust if some training points can have really high influence on it. And like Se-Woong has done a bunch of cool work on trying to relate these robust statistics and differentially private notions together as well.
Thanks.
Joe, want to unmute yourself? Ask your question.
Hey, yeah, this is really cool stuff. I was curious if you ever experimented with how this generalizes to like examples where you explicitly specify importance with sample weights. Like how can you then like tweeze apart the influence due to the explicit importance versus like the implicit importance?
Yeah, good question. So Joe's asking about, what if you have a weighted data set, right? So for example, if you know that maybe some classes of points are a minority, you might want to upweight them. So the math sort of goes through pretty straightforwardly in the sense that the additional weights just multiply onto the influence. So you can think of the influence as a product of the explicit importance weights and the sort of implicit influence of that point. Yeah, so that's maybe a related question, which is, can we use can we use these notions of influence to train better models, right? So for example, if I say, oh, I think these two training points are very similar to each other, so I want them to have the same effect on the model, right? Basically as a way of giving additional supervision to the models using these weights. And that's also like a pretty interesting idea that has been explored a little bit by people, but the problem is that specifying this sort of pairwise similarity or influence is difficult because it's sort of n by n, and so there's one technical challenge there.
Any other questions?
I guess I can ask one. So I'm curious whether any of your work has led you towards like different approaches or ideas about building good data sets just in general, right? So if you want to build some kind of robust data set, do some of your ideas give you a sense about how to do that better? And this is also a little bit related. I think the waterfowl example you gave me, you gave in your talk, made me think of boosting, right? Somehow it seems like the thing you really needed to do there was like recognize some sub portion of your data set on which your performance is really a lot worse, and sort of focus on that. If there's anything you can comment about that.
Yeah, thanks. Both of these are great questions. So let me start with the first one on data set collection. So I think one important thing for data set collection is that this metadata is really important, right? It's used widely in practice. People do collect it. And when we were constructing Wilds, actually, we struggled quite a lot with some data sets that looked like they ought to be very good fits. Like they were medical data sets collected across different hospitals or face data sets from different groups, but there was just no metadata there. So we couldn't split the data set in the ways that we wanted to that would reflect the actual shifts that happen in practice. So that's one thing. And another is when we are constructing these sort of static data sets, right? I think being cognizant of what kinds of shifts are likely to arise in deployment, and then can we reflect that in the data set structure is also very important. Right? So for example, in this camera trap data set, if you, actually I think Ludwig found this out, but pointed this out, but if you, like within one camera, some of the images are really similar, right? Because they might be just actually the same animal, maybe at different times or something, and from the same angle. And so if you just split this data set IID, like in the standard way, then you might get very inflated performance, right? But in reality, we will want to try to deploy it to new cameras, and that is a very different story. So I think designing the data set that way. Also, the evaluation metric that we use to hill climb on the data set is important. So for example, in this case, we are using macro F1, which makes the rare species more important, right? As opposed to like average accuracy. And this is important because for this application, what people care about is the rare species. And so average accuracy might mask that effect. And basically like aligning the data set metrics and structure to the real problems is important. You also asked about the waterfowl example and group DRO. So this is a great question. So our approach was to use predefined groups, right? Actually, that's similar to the active sampling approach here. You know the demographics and you want to do a min-max over them. Traditionally, a lot of DRO techniques don't use these predefined groups, right? As you know. So for example, there's this classic formulation called the value at risk or conditional value at risk. And what that does is that the user specifies some fraction of the data set, say 5%. And then instead of minimizing the average loss, it minimizes the loss on the worst 5% of data points, right? So and this is conceptually very nice because if you can do well on that, you are guaranteed good performance against any subpopulation of size 5%. You don't need to know it in advance. And the problem is that sometimes it can be too conservative, right? Because maybe 5% of your data is mislabeled. And then if you try to optimize that, it's just your model doesn't learn anything. And so we're trying to strike some middle ground here where we rely on these annotations to give additional structure so that we know which groups to optimize for.
Tim, did you have a question?
I did. Thank you for the great talk. Actually, at the very end, you got exactly into my question. I was curious about what you can do when you don't have those explicit groups available. And you started talking about, for instance, working on the bottom 5%. So you already started talking about it. I'd be curious if you could talk more about kind of where those kind of worst performing 5% techniques can fail. Thank you.
Yeah. Good question. So yeah, they can fail when things are just like a bit noisy, right? So because in real data sets, even in very standard ones like MNIST or CIFAR and so on, there is a bunch of label noise. So we do expect some small, even if you have a perfect model, you expect some level of high loss on some subset of the points. And so this makes these sort of agnostic methods that don't require any group information like hard to get to work on them. in general, we haven't been able to. So we've tried a bunch to remove this training, these group annotations. In general, the methods haven't worked. We have in this, the last paper on this slide, the Just Train Twice, we sort of make a little bit of progress in this direction. And what we do here is we assume that we don't have the group information on the training set, but we still make use of it on the validation set in order to choose hyperparameters and do model selection. And this turns out to be pretty crucial. There are actually a bunch of papers that purport to solve like the Waterbirds problem and so on without group information. But if you look carefully, all of them use the group information on the validation set to select the hyperparameters. And that's partially because of this trade-off here between average accuracy and worst group accuracy, right? So because of this trade-off, which we would like to avoid, but right now methods have a trade-off, and this means that if you select models just based on average accuracy, you tend to get the ones that are not as robust to small groups.
Thank you.
Yulia, you want to ask your question?
Hi, Peng-Wei. Thank you very much for your talk. I'm a big fan of your work. I had a question about influence functions and in general on using them, on a hope to use them to interpret decisions of large pre-trained models. Do you have any thoughts? I understand that it's currently infeasible, but do you have any thoughts on how can things be approximated? How can they be used?
Yeah, thanks, Yulia. That's a great question. So you know, I'll like even just writing out the Hessian for these large models is just completely infeasible, right? And much less inverting it. So there have been a bunch of ways people have tried to tackle it. And so in NLP, I think there have been a couple of papers that basically just freeze the last layer. So you assume a fixed representation and you just look at the influence on the last layer, then it's nice and convex. So that's one. There have been other ways that sort of approximate influence. So there's a method from Google that just trains the model normally using SGD, and then it counts how much update each example costs, and it uses that as a proxy for influence. So that's another thing. More recently, Alexander Madri's group at MIT, they have this data models paper which is pretty interesting. It feels almost like a compressed sensing approach to influence. So they basically make use of a lot of GPUs and their fast data loaders to train many, many models. And for each model, they leave out a random subset of points. Okay? And then they assume that, like with influence, that each example contributes linearly towards the prediction. And so you can imagine you now have this matrix where you have each observation is like a random subset of points was left out, and you see the prediction, and then you have a lot of these, and you want to back out the influence of each point. And that seems to actually work quite well at the cost of like significant amount of compute. So you might imagine that, let's say, maybe not for pre-training the language model, but let's say for fine-tuning it on some task, right? We could take a similar approach.
Thank you.
Great. Well, thank you very much for the talk and the questions. I'm sure Peng-Wei will be able to take some questions offline if you contact him. And let's thank the speaker again.
Great. Thank you for the questions and for inviting me here. Please feel free to drop me a line if you have any follow-ups.